Welcome to Lesson 4.4, Training Your First Model. Overview. Varial. This is the moment everything has been building toward. Your model is configured, your data is prepared, and now you're going to watch a neural network actually learn in real time on your own hardware. You'll see the loss curve drop, interpret what the training logs are telling you, and by the end of this lesson, you'll have a fine-tuned model saved to disk. Plan for about 30 minutes of setup and anywhere from 30 to 90 minutes of training time depending on your dataset size. Learning objectives. By the end of this lesson, you'll know how to kick off a training run and read what the output is actually telling you. You'll be able to interpret the loss curve, spot the warning signs of overfitting or divergence, and make the call on when to stop. You'll also understand what training speed to expect on the Tesla P40, and you'll have your trained model saved and ready for evaluation. Starting training. Here's the complete training pipeline. Everything from lessons 4.1 through 4.3 assembled into one script. This script is your full end-to-end training pipeline. It loads the llama-3.2-3b-instruct model from unsloth using 4-bit quantization, that's the load_n_4-bit flag, which cuts memory usage dramatically and is what makes a 24 GB card like the P40 viable for a 3 billion parameter model. From there, it attaches LoRa adapters, which means instead of retraining every weight in the network, you're training a small set of low-rank matrices that steer the model's behavior. The script then loads your training and validation JSON files, applies the chat template so the data is formatted exactly the way the model expects, and configures the SFT trainer with your batch size, learning rate, and evaluation strategy. When training starts, you'll see GPU stats and a live loss readout. The final summary gives you training time, samples per second, and the closing loss value, your first concrete signal of how well the run went. Structure your notebook at notebooks/03-first-training/03-train.ipnb with one cell per logical stage. Cell 1 for imports and setup, cell 2 to load the model, cell 3 to attach LoRa adapters, cell 5 to configure training arguments, cell 6 to create the trainer, and cell 7, the one you've been waiting for, to actually start training. Understanding training output. Once training starts, your terminal will fill with a table of metrics updating every few steps. Each row shows the current step, the training loss, the learning rate, and the speed in iterations per second. The most important column is loss. You want to watch it trend downward across the full run. The evaluation block that appears at the end of each epoch is equally important. It shows how the model performs on data it has never seen, which is your real signal of whether learning is actually generalizing. A final training loss around 0.87 and a total runtime around 1234 seconds are reasonable numbers for a first run on this hardware. Training loss is the model's error signal, numerically, how wrong its predictions are on the training data. A steadily decreasing loss means the model is learning. If it plateaus very early, the learning rate is probably too high and the optimizer is overshooting. If the loss jumps around erratically, try a lower learning rate or a larger batch size to smooth the gradient estimates. If the loss starts climbing, the model is diverging. Stop immediately and lower the learning rate before restarting. Here's what a typical loss progression looks like across a run. At the very start of training, loss typically sits between 2.5 and 3.0. That's the model making near-random predictions. It hasn't learned anything task-specific yet. After a few hundred steps of fine-tuning, you should see it drop into the 0.5 to 1.5 range, which reflects genuine learning. The best values you can realistically achieve in the 0.1 to 0.5 range come with risk. At that level, the model may be memorizing training examples rather than generalizing from them. Watch your validation loss closely as training loss gets very low. The learning rate column shows you exactly where you are on the optimizer's schedule. With a cosine decay schedule, it follows a characteristic shape. Training opens at 2e4, the peak learning rate, after a short warm-up phase where it ramps up from 0. That warm-up prevents large destabilizing weight updates in the first few steps when the gradients are noisy. Through the middle of training, the rate eases down to around 1.5 e-4, allowing finer adjustments. By the final steps, it's down to 5 e5, making only small corrections as the model converges. If you see the learning rate column holding flat or behaving unexpectedly, double-check your scheduler configuration. It's a common source of subtle training bugs. The iterations per second metric tells you how efficiently your hardware is being used. On a Tesla P40 with Llama-3.2-3B and a batch size of 4, expect 1.0 to 1.58/s. Drop to Llama-3.1-8B with a batch size of 2 and that falls to 0.5 to 0.8/s. Windows will run about 10 to 15% slower than Linux on identical hardware. That's a known overhead from the Windows CUDA driver stack, not a sign anything is misconfigured. Evaluation loss is the metric that actually tells you whether your model is learning or just memorizing. If eval loss is lower than training loss, the model is generalizing well. That's the ideal outcome. If they're close, that's fine. If eval loss is substantially higher than training loss, you're looking at overfitting. The model has learned to reproduce the training examples but can't handle new inputs. That's your cue to intervene. Training time estimates. With a batch size of 4, gradient accumulation of 2, and a max sequence length of 2048, here's what to expect on a Tesla P40. 50 examples over 3 epochs, 10 to 15 minutes. 100 examples, 20 to 30 minutes. 200 examples, 40 to 60 minutes. 500 examples, 90 to 120 minutes. 3 variables push that time up or down significantly. Sequence length has the biggest impact. Doubling the length roughly doubles the compute. Larger batch sizes speed things up if the memory is available. Gradient checkpointing saves memory but costs about 15% in speed, which is usually a worthwhile trade on a 24 GB card. Monitoring training. Calling write single quote trainer.train as is the single line that starts everything. The moment you run it, the progress bar appears and the metric table begins updating. Those logs aren't decoration, they're your feedback loop. Watch the loss column at every logged step. Check the eval block at the end of each epoch and keep an eye on your GPU utilization in a separate terminal. If the progress bar stalls or the GPU drops to 0% utilization, something has gone wrong upstream and you'll want to catch it early. The training log table gives you a snapshot at every logged step. Train loss is your primary signal. Watch for a consistent downward trend. The LR column confirms the cosine schedule is working. You should see it decrease gradually across the run. The H/S column tells you whether the GPU is fully engaged or throttled. The most critical row in the entire log is the eval loss entry, which appears at the evaluation interval you configured. That number, the model's performance on held out data, is what determines whether you have a model worth keeping or a model that's overfit to your training set. Run this PowerShell loop in a separate terminal while training is active. The NVIDIA dsmy command queries your GPU hardware directly, and the infinite loop with a 2-second sleep gives you a live dashboard without hammering the driver. ClearHost keeps the output readable by refreshing the screen on each iteration. In the output, focus on 3 numbers: memory used versus total. You want to stay below 22 GB on a 24 GB card to avoid OOM errors. GPU utilization percentage, which should be in the 90s during active training, and temperature, which should stay comfortably below 85 degrees Celsius. If utilization drops to zero mid-training, the GPU is waiting on the CPU, usually a data loading bottleneck. When to stop training? Vad jól this it's consummita by it's a ponsumstamai tamtisokastam itso katata. This is the overfitting signature, and it's one of the most important patterns to recognize. For the first few epochs, evaluation loss drops steadily alongside training loss. The model is genuinely improving. Then at epoch 4, eval loss ticks upward even as training loss keeps falling. By epoch 5, the gap has widened further. What's happening is the model has shifted from learning generalizable patterns to memorizing specific training examples. The checkpoint from epoch 3, the last point before eval loss reversed, is your best model. That's the one you want to save and use. The action here is clear. Stop training and roll back to the epoch 3 checkpoint. That's why saving checkpoints throughout training matters. Without them, you can't recover the best version of your model. A training loss of 0.05 paired with a validation loss of 2.50 is a textbook overfitting case, and a severe one. The model has essentially memorized the training set. It can reproduce training examples with very low error, but it has lost the ability to generalize. The gap between those two numbers is your diagnostic signal. Solutions include stopping training earlier, adding more diverse training data, increasing dropout to regularize the model, or reducing the learning rate to slow down the memorization process. A loss that drops from 1.2 to 1.15 and then flatlines at 1.14 across subsequent steps is telling you one of two things. Either the learning rate is too small to make meaningful progress, the optimizer is taking steps so tiny that the loss barely moves, or the model has genuinely converged and there's nothing left to learn from this data at this configuration. The diagnostic is timing. If this plateau happens in the first quarter of training, increase the learning rate and restart. If it happens near the end of a full run, the model is done. Save it. Periodically during training, not just at the end, feed the model a test prompt and look at what it generates. This is your qualitative check alongside the quantitative loss metrics. A model can have a reasonable loss value but still produce incoherent output, or vice versa. Look for coherence, relevance to the prompt, and whether the response style matches what you trained on. If the outputs are already good at epoch 2, that's a signal to stop. Continuing to train past the point of good output quality is how you end up with an overfit model. Handling errors. A CUDA out-of-memory error means the GPU ran out of space to hold the model activations, gradients, and optimizer states simultaneously. On a 24 GB P40, this usually happens when the batch size is too large for the sequence length you've configured. The error itself is harmless. Nothing is corrupted, but you need to free the GPU memory before retrying. Work through the fixes in order. Reduce per underscore device underscore train underscore batch underscore size, then compensate by increasing gradient underscore accumulation underscore steps to keep the effective batch size the same. Then reduce max underscore sac underscore length to 1024 if you're still hitting the limit, and confirm that gradient underscore checkpointing equals. After an out-of-memory crash, the GPU holds onto allocated memory even after the Python process that caused the error has stopped. Write single quote torch.cuda.empty underscore cache excess releases that run this line, then restart your Jupyter kernel entirely, not just the cell, and rerun your training script from the top. Restarting the kernel is the critical step. Without it, PyTorch's internal memory allocator still thinks some of that memory is in use, and your adjusted batch size may still fail. A loss value of nan, not a number, means the model's computations produced an undefined result, typically an infinity that propagated through the network. The most common cause is a learning rate that's too high. The weight updates overshoot so dramatically that activations explode. It can also be triggered by corrupted training examples containing values that produce numerical instability. Check three things. Lower the learning rate from 2E4 to 1E4 or 5E5. Increase warm-up steps to give the optimizer more time to stabilize at the start. And inspect your dataset for any malformed examples that might be feeding bad values into the forward pass. If training appears to be running but the GPU sits at 0% utilization, the training loop has stalled, most likely in the data loading stage. On Windows, the default multiprocess data loader can deadlock when accessing certain file paths. The fix is to add data loader underscore num underscore workers equals sign 0 to your training arguments, which forces data loading onto the main thread and bypasses the multiplies issue entirely. Also run print len train dataset to confirm your dataset loaded correctly. If it returns 0, the JSON path is wrong and the trainer is silently iterating over nothing. A device mismatch error means part of your computation graph is on the CPU while the rest is on the GPU. Unsloth handles device placement automatically in most cases, but if you've manually manipulated the model or inputs outside the standard training loop, you can end up with this. The fix is straightforward. Calling model.toCUDA moves all of the model's parameters and buffers onto the GPU. There's no output when this succeeds, it just works. You can verify placement afterward by checking next model.parameters device, which should return CUDA 0. If you're using Unsloth's fast language model, this should already be handled for you, but it's a useful diagnostic step when you're chasing a device mismatch error and need to confirm where the model actually lives. Saving during training. Athena satas, vaye interfere. Dette care. Sapatino sapatida satas. Saving during trainings quickly. With save strategy steps and save underscore steps equals sign 50, the trainer automatically writes a checkpoint every 50 training steps. Here's what that directory structure looks like. Each checkpoint directory is named after the step at which it was saved. Checkpoint -50, checkpoint 100, and so on. Inside each one, 3 files do the work. The right single quote adapter underscore model dot save tensors right single quote file contains the trained LoRa weights. This is the actual learned knowledge. The right single quote adapter underscore config, the right single quote trainer underscore state dot JSON right single quote file captures the optimizer state and current epoch, which is what enables you to resume training from a checkpoint rather than starting over. If your machine crashes mid-run, these checkpoints are what save you. This saves the current model and tokenizer state to a directory you specify, in this case outpost/manual underscore checkpoint. Calling save underscore preprimed on both the model and the tokenizer is important. The tokenizer config needs to travel with the weights so that inference later uses identical tokenization. There's no terminal output on success, so after running this, navigate to the output folder and confirm the files are there. You should see the adapter weights, the config JSON, and the tokenizer files. If the folder is empty or missing, check that your output path doesn't have a permissions issue, a common friction point on Windows. Complete training notebook. This is the complete notebook, everything assembled into a single runnable sequence. Cell 1 imports the libraries and loads the llama-3.2-3b-instruct model with load_in_. The subsequent cells attach LoRa adapters. load and format your training and validation datasets, and configure training arguments with the learning rate, batch size, evaluation strategy, and gradient checkpointing. The SFT trainer wires all of those pieces together and manages the training loop. When the final cell completes, the model and tokenizer are saved to disk. The output at each stage should confirm successful loading. Watch for any warnings about missing weights or mismatched configurations, as those are early indicators of a setup problem before you invest training time. Training completion checklist. Before moving on, run through these confirmation points. Training should have completed without a crash or error message. The loss curve should show a clear downward trend with a final training loss below 1.5. Higher than that suggests the model didn't have enough time or the learning rate needs adjustment. The validation loss should be in the same ballpark as training loss. A large gap means overfitting. Check the outputs directory for checkpoint folders and the final saved model weights, and confirm your training logs are accessible. You'll want them when you start evaluating and comparing runs in the next lesson. If all of that checks out, you're ready to move forward. Key takeaways. 7 things to carry forward from this lesson. Watch your loss. It should trend downward, not plateau early or spike. Monitor validation loss alongside training loss to catch overfitting before it gets severe. Budget 30 to 90 minutes of wall clock time and don't expect instant results. Save checkpoints throughout so you can recover the best model state if something goes wrong. Stop early if the outputs are already good. More training past that point hurts more than it helps. If loss hits NaN, your learning rate is too high. Cut it in half and restart. And test the model's actual output periodically, not just the loss number. The two don't always agree. What's next? Training is complete. The next step is finding out whether the model actually learned what you wanted it to learn, and that means systematic evaluation. Continue to lesson 4.5, evaluating and testing results. Additional resources. Tasura. For deeper reading, the SFT trainer documentation covers every training argument in detail. The Unsloth training tips page has hardware-specific guidance for getting more speed out of your setup. And the debugging training guide is worth bookmarking. When a run goes sideways, it's the fastest path to a diagnosis. You've just trained your first fine-tuned model. That's a real milestone. This chart compares 3 learning rate schedules: cosine decay, linear decay, and a constant rate. Cosine decay, the recommended choice, starts high to allow rapid early learning, then curves smoothly downward, which helps the optimizer settle into a good minimum without overshooting at the end. Linear decay drops at a fixed rate, which works but tends to reduce the learning rate too aggressively in the early stages when the model still has a lot to learn. A constant learning rate never adapts, which can cause the optimizer to keep making large updates even when the model is close to convergence. For fine-tuning with LoRa, cosine decay is the default in Unsloth for good reason. It matches the natural learning curve of the training process. This plot shows how LoRa rank affects the loss curve during training. Each line represents a different rank value: 4, 8, 16, 32, and 64. Notice that lower ranks converge faster early in training, while higher ranks improve more slowly but can ultimately reach lower loss values given enough steps. The practical implication: rank 16 is a strong default that balances convergence speed with model capacity. If you're working with a small dataset, a lower rank like 8 reduces the risk of overfitting. If your task is complex and you have abundant data, pushing to rank 32 or 64 can squeeze out additional quality, but expect longer training times and higher memory usage. This diagram shows how gradient accumulation lets you simulate a large batch size without holding all the samples in GPU memory at once. With per_device_train_batch_size equals sign 4 and gradient_accumulation_steps equals sign 4, you process 4 microbatches. After all 4 microbatches have been processed, you execute a single optimizer step, equivalent to what you'd get from a batch of 16. The weights update once per effective batch, not once per microbatch. This is how you get the training stability of large batches on a 24 GB card without triggering an out-of-memory error. This heat map shows final training loss across a grid of learning rate and batch size combinations. The axes range from learning rates of 5E5 to 3E3 and batch sizes from 4 to 32. The lowest loss values, around 0.52 to 0.55, cluster around moderate learning rates and smaller batch sizes. The highest loss values appear at the top of the learning rate axis, where rates like 3E3 cause instability regardless of batch size. The takeaway is that learning rate has more leverage over the final loss than batch size does. If a run isn't converging, adjusting the learning rate is almost always the higher impact intervention. This chart illustrates two warm-up strategies: a linear warm-up that holds at a constant learning rate afterward, and a linear warm-up followed by cosine decay. The warm-up phase, ending at the dashed orange line around step 30, exists to protect the model from large destabilizing gradient updates at the very start of training, when the LoRa weights are randomly initialized and the gradients are noisy. Without warm-up, the first few steps can push weights into bad regions that take many steps to recover from. After warm-up, cosine decay gradually reduces the learning rate, which is why the green line outperforms the flat blue line in most fine-tuning scenarios. These two graphs show the trade-off that comes with increasing LoRa rank. On the left, quality improves significantly as rank increases from 4 to 32, then levels off. The gains from rank 64 and 128 are marginal compared to the jump from 4 to 16. On the right, the number of trainable parameters grows with rank, with a notable spike at rank 32. The practical conclusion: rank 16 sits near the knee of the quality curve while keeping parameter count manageable. Going higher than 32 gives diminishing quality returns at increasing memory and compute cost. Usually not worth it unless you're working on a particularly complex task with a large, high-quality dataset. This table compares 5 optimizers across memory usage, speed, and recommended use case. AdamW 8-bit is the default for QLoRa training, low memory, fast, and well-tested. AdamW 32-bit is faster but memory-hungry, making it practical only for full fine-tuning on cards with 40 GB or more. SGD with momentum is the fastest option but converges more slowly, which makes it better suited for continued pre-training than task-specific fine-tuning. Lion is experimentally promising, similar behavior to AdamW with lower memory, but less battle-tested. Adafactor uses the least memory of any option, at the cost of moderate speed and convergence reliability, making it the choice when memory is the hard constraint. For your P40 setup with QLoRa, AdamW 8-bit is the right default. This table maps out effective batch sizes across different combinations of per-device batch size, gradient accumulation steps, and GPU count. The effective batch size is the product of all three: per-device size multiplied by accumulation steps multiplied by the number of GPUs. With a single GPU and 4 accumulation steps at a per-device size of 4, you get an effective batch of 16, the recommended starting point. The VRAM requirement scales with per-device batch size, not effective batch size, which is exactly why gradient accumulation is so valuable. You get the optimizer stability of a large batch without the memory cost. With two P40s in your system, you can double the effective batch size at the same per-device memory footprint. The learning rate finder sweeps through a range of learning rates on a log scale and plots the resulting loss at each value. The loss decreases as the learning rate increases up to a point. Then it bottoms out and starts climbing sharply as the rate gets too high and training destabilizes. The optimal learning rate sits just before that minimum, around 2E4 in this example. That's the sweet spot where the optimizer moves fast enough to make real progress, but not so fast that it overshoots. Running a learning rate finder before a long training run is a small time investment that can save you from a multi-hour run at a suboptimal rate. This reference card summarizes the key training parameters for your first run: per_device_train_batch_size of 2 keeps memory usage conservative. Increase it to 4 if your GPU has head. Gradient_accumulation_steps of 4 brings the effective batch size to 8, giving the optimizer stable gradient estimates. A learning_rate of 2E4 is the standard starting point for LoRa. Drop to 1E4 if you see instability. 3 epochs is a solid starting point. Adjust between 1 and 5 based on your dataset size and how quickly the loss converges. The warm-up underscore ratio of 0.03 dedicates the first 3% of steps to ramping up the learning rate. Cosine scheduling, BF16 precision, and gradient checkpointing are all enabled for memory efficiency. Log every 10 steps to get a clear picture of the loss curve. Save checkpoints every 50 steps, and cap sequences at 2048 tokens. These defaults are tuned for the P40. Treat them as a starting point and adjust based on what your loss curve tells you.